Hello, everyone, and welcome to Ceph Storage in a world of AI ML workloads. This is Michael Hord, your host and facilitator for today's discussion. I serve as chair for the SNIA Cloud Storage Technologies CST community. Today's conversation is with Kyle Bader, who is Principal Portfolio Architect at IBM Storage. Hello, Kyle. How are you?
Hello, everybody.
Great. Next, we have Phil Williams, who is a product manager at Canonical. How are you, Phil?
Hey, Michael. Hi, everyone. I'm great. Thanks.
Awesome. So before we get started, I want to mention that SNIA is a group of about 200 industry-leading organizations comprising of 2,000 active contributing members and 50,000 participating IT end users and storage experts worldwide. SNIA develops global standards and delivers education on all technologies related to data. As one of the organizations within SNIA, the CST is dedicated to education on topics like Ceph, the Linux of storage today, and AI ops, reactive to proactive. In September at SDC 24, the CST created and hosted the world's first cloud object storage PlugFest. We successfully established two outcomes. First, we created the PlugFest community around 3 days of cloud object storage testing and a birds of a feather BOF session to collect industry feedback on next steps. Based on demand among this new community, we kickstarted the SNIA Cloud Object Storage Test Tools group, which will work to create best practice test suites to help automate compatibility testing around popular cloud API protocols like AWS S3. Please go to this PlugFest link to join this important effort. Before we get started, let's take a look at the SNIA legal notice. This provides SNIA's copyright notice regarding use of the material. There are no warranties expressed or implied, so if you want to reference this material, please do so at your own risk. You can download a copy of this presentation using the interface for this live webinar. The interface also allows you to submit questions during the talk and rate this presentation at the conclusion. We really appreciate your questions and feedback. So for today's discussion, Kyle and Phil will address AI workloads regarding training, performance, checkpointing, and inference, as well as Ceph storage, how Ceph storage meets the need of AI deployments, and how to increase storage efficiency through acceleration and network scaling. Then we will have an informal Q&A session, and we hope you in the audience will submit questions for our experts. If we're not able to cover all the questions during the session, we will answer your questions in a Q&A blog, which will be posted after this webinar. So let's get started. Phil, please take it away.
Thank you again, Michael. And again, hello, everybody. So I think the important thing to do here is kind of just dive into this world of AI and what it actually means in terms of data. So I think let's think about the different types of data you find in a typical AI system. And what's also kind of interesting to point out now, and you'll probably see this revealed as we go through the slides today, is that not all of the different data sets use the same kind of access methods. So that's going to become kind of important as we get a little bit further into kind of the why Ceph and why Ceph's involved in all of this stuff. So let's start with that workload, or the workload or life cycle. So where do we start? We start with inputs. We call that raw data. I guess that's kind of self-explanatory. But you can think of that as really as just like unstructured data, unstructured content. So video, audio, text, email, chats, telemetry, like every IoT device on the planet uploading some kind of information to some kind of quote unquote cloud somewhere. This ends up in kind of like a data or a data lake, or just an object storage repository. So just imagine all of that like unstructured information that could potentially go into an AI workload. So we take all that raw data. What do we do with it? We kind of sort it. We have to organize it. We have to catalog it. So we take the raw data, we catalog it, and then we start using that kind of stuff for things like pattern matching. So imagine you're training a model, and that model is to recognize license plates on cars. So essentially, that catalog raw data is going to be like good examples of what a license plate or number plate looks like on a vehicle. Nice, clean, clear images that we've been able to sort of manually sort. We then take that nice organized data, and that's when we can start feeding it into a model, start training a model from that data. During that training process, it's very, very storage intensive. You're going to be reading a lot of this raw data and this training data to be able to start building that model out. But then also on the back end of that, once you have your model, you need to store that somewhere for future use as well. So that's going to typically be something like a shared file system somewhere. So that can then be reused in future doing things like inference and in that kind of results phase. So there's a whole bunch of steps to get to this point where you have a model, you have nice data, you can then take an incoming stream of data. So in that results portion of this, it feels like it's taken a lot of time to get there. You want to actually then be able to use that information for business decisions, right? So say that license plate example, you want to do that in real time for, like a toll road, something like that, or credit card transactions. You want to be able to detect fraud, those kinds of things. What's interesting there is that you might not even actually store the model in a centralized storage system. That might actually be in something that's a bit more distributed, so you have low latency. So in this entire life cycle, there's lots of different types of storage in use, or different ways of accessing storage in use. So one of the things we want to highlight is kind of the flexibility of Ceph and being able to answer a whole bunch of those things. And then I think just finally, there is one area just to sort of think about is also this like ongoing iterative process. So we might train a model once, but actually in the future, we may adjust it, we may tweak it. We want to go back and retest it. So that training data, once we've kind of organized it, we want to like freeze that in time. We want to be able to use those same data sets to prove whether a model is like good, better, got worse, after we've done any kind of adjustments to that. So this is where things like snapshots, object versioning kind of enters the picture. So then what makes AI storage needs special? So let's take a look at a typical GPU. So from a compute perspective, a single card peaks around 4 petaflops. Doesn't really mean much to us storage folk. So let's kind of think about that from a bandwidth point of view. So to keep that thing highly utilized and running it effectively, we need to feed it around 5 gigabytes per second. So that's a single card. This is kind of another like jump in computer architecture where we've introduced a new component that's kind of like a leap beyond the other components in the system. Kind of like what happened with moving from spinning media into NVMe, where you were no longer waiting for the disk to provide you with data. You're now waiting for the CPU to kind of catch up with this super speedy storage medium. So let's start scaling this up. So I talked about that one GPU. So now if you think about a system that could have up to 8 GPUs. So the typical recommendation there is that single system now needs around 20 gigabytes a second just to keep all of the GPUs in that system highly utilized. It's not shown here, but there's another leap. So take, for example, NVIDIA, they have a super pod concept. That's actually up to 256 GPUs as like the base entry model. It scales further than that. So imagine 256 GPUs with this kind of demand. You're looking at something like a terabyte per second of read bandwidth. I think back to when I started in the storage industry, and that was crazy talk. Now it doesn't feel all that. It still feels kind of crazy, but it's this kind of leap that has happened. The other thing to think about as well in these kind of nodes, there is a bunch of local NVMe typically. And the reason for doing that is a lot of training does involve a lot of rereads. So if you're able to have a localized cache, that obviously alleviates some of the pressure on the shared storage system as well. So now that we have a kind of an initial quick understanding of some of the challenges, what actually happens when we want to create a model. So at this point, I'll hand over to Kyle, who's going to start talking us through Granite 13Bs, checkpointing, and a bunch of other topics.
Clicked one too far there. All right, thanks, Phil. So I wanted to talk a little bit about like the size of training corpuses, and I wanted to start with LLMs because they are kind of the topic du jour. And so, as an example, here I have what at IBM they call the data pile that represents the training data that was used for the Granite 13B model. And it gives you kind of a good gauge of size. So the actual raw, like the raw corpus before they've done anything to it is, just under 30 terabytes of data. But then they do some additional processors where they remove deduplications, they remove kind of like HTML markup from Common Crawl and profanity and all this other stuff. And then they get down to this, relatively small, like around 8 terabytes worth of data, and then they, that all gets tokenized, and that's what actually feeds the GPUs during training. If you look at like the papers around GPT-3, the actual raw data bit, they went through a similar process where the actual raw data was around 45 terabytes, and then that really got filtered down to about 570 gigabytes that was used for the training. And you can see that there's this correlation with the number of tokens and the actual size. And there's a couple links here for people that are kind of interested in learning more about those processes and the anatomy of these different sorts of data sets. Checkpointing is a very key consideration in machine learning models, and it's kind of a really interesting area of active development. When you are checkpointing a model, you're basically saving a combination of the weights for the model and the optimizer states. So to estimate the size of a checkpoint really depends on the precision of the weights and what optimizer is being done and the parameter count. So like, for example, these kind of estimated checkpoint sizes are based on the use of the atom optimizer, which uses about 12 bytes per parameter. And then we get to these different sizes based on the different scales of models, right? So, we have the 13 billion Granite model here, and then the 70 billion Llama, 175 billion GPT-3, Llama, Llama 3, the flagship, 405 billion, and then those are all. So those four, those are all examples of large language models, and you can see, the parameter sizes and the estimated checkpoint sizes. But I put in another one in there, which is there's a Facebook paper in here, and they talk about DLRM, which is in fact a recommendation system model. And you can see that the number of parameters in that is significantly larger, and so it's going to have a significantly larger checkpoint. And to give people an idea of like what this means in terms of throughput is if you took like 35 gigabytes a second worth of throughput, how long would it take to do these checkpoints, right? And it's not perfect too, because it depends on the data level, the amount of data level parallelization and the pipelining that they're using for training in terms of like how many streams are writing. So in some cases, maybe the storage system could do more IO if there was more parallelization. But just kind of like to just give a rough comparison, like when you're looking at these and you go, oh, okay, 5 seconds, 28 seconds, 70 seconds, those are all, kind of fairly reasonable. As you get into the other ones, those are starting to get bigger, to be kind of bigger numbers. There was a really interesting article or paper done about like how long a checkpoint should take relative to the amount of compute. And I think they came up with a number around 10%. In the case of these GPUs and the GPU clusters, they represent a significant capital expenditure. And so the amount of time that you can minimize where you're not doing work because you're checkpointing is of paramount importance. And so there's some interesting work where people are doing things like this check and run paper that was here, where one of the things that they're doing is they're doing kind of differential checkpoints. There's also some recent things that have been done. So this reducing checkpointing times link on here discusses how there's a new asynchronous checkpoint mechanism in PyTorch And what that effectively does is, you have your forward propagation, then you have your backward propagation, and then you have the optimization. And then at the point of the optimization, immediately after that, it destages the contents of GPU memory into CPU memory, and then they can start on the next. Basically, they can start on the next phase of the training, or the next epoch of the training, while asynchronously the checkpoint is dispatched down to storage, and that allows that checkpoint to continue to occur while the next kind of training epoch is progressing. And so, as long as that checkpoint finishes before the next epoch gets to the point where it needs to do its checkpoint, then you can kind of take this time that it takes to do the checkpoint and hide it so that it's not kind of in the critical path anymore. And so, like, there's a lot of work, a lot of interesting stuff that's happening in terms of checkpointing, and it's something to look out for. But yeah, there are some techniques now that help you kind of get storage out of the critical path, and you can perhaps get away with a little bit less crazy of a storage system.
Kyle, we have a question from the audience. I think you might have answered it already, but the question is, what is the realistic checkpoint frequency? And if you could just touch on that.
Yeah, I think it depends, right? So it depends on the organization. I'm trying to think what it was. They wanted it to, so that they wanted to be about 10 point of the checkpoint time. There are different organizations that will, do it every, 10 rounds or every 100 rounds, or in some cases people do it like twice a day or something. I think the goal though is, like, if we can progress the state of the art when it comes to checkpointing and the storage systems that are absorbing the checkpoint to where you can do a checkpoint after every epoch, that is, of course, the goal. So if you can get to the point where, through methods like the asynchronous checkpointing, differential checkpointing, and having a sufficiently sized storage system to where you could checkpoint after every epoch, that's the gold standard, right? The reason why you want to checkpoint as frequently as possible without, like, compromising that, how much time is spent for compute versus checkpointing, is because, especially as these GPU environments scale to, thousands of GPUs, the chance that you'll have a failure during of a GPU or some other component in the training cluster goes up. And so, like, as the training environment scales, you need to increase the checkpointing frequency.
Okay, great. And then one other kind of high level question. If you could briefly just address how cost effective are GPUs in terms of performance and getting this job done.
How cost effective are GPUs?
Yes, and in comparison to other things, go ahead. Like if you were to use CPUs or things like that.
Oh, I mean, I think for any of the, like, really intensive training, it's going to be on GPUs. It's just more
Right.
electrically efficient, right? Like, the amount of matrix multiplications that you can do in parallel is just, you just can't do that.
Right, and it's also a timeliness. How critical is that workflow for production, and just the feasibility of getting the work done on a reasonable schedule? GPUs would certainly be the top pick. So,
especially for training, yeah, there are certainly like inference activities that you can do with that you can do comfortably on CPU, especially if you use some of the model quantization type things that change the precision of the models to, so that they're int 8 or something, and then they can be more effectively, you can more effectively run those sorts of inference things off of CPU. But you have to make sure that by doing that quantization, that the quality of the inference still meets the requirements for the use case, right? So it might be, in some cases that it's fine. In other cases, you might need the higher precision, and in which case you might that might push you towards using more accelerated hardware.
Great, thank you.
So on this next slide, I wanted to kind of, LLMs are all the rage, but I also wanted to make mention of recommendation systems, because recommendation systems are perhaps some of the largest in terms of parameter count. We saw that on the previous slide with the 1 trillion parameter, and most demanding in terms of checkpointing, but they also have far more data that they're trained off of. So when you look at LLMs and you look at that, the Granite model training set or the training data set for GPT-3, they're measured in gigabytes or a few terabytes, whereas recommendation system is often trained off of petabytes of data that is housed in kind of like a data lake. And so in this example, you have an application that's generating events and features, right? So an event might be like the actions of a user on the web page. So when they add a product to their cart or something, and then features are things about about the user itself, and then these are kind of flowing in through some sort of streaming engine, and then there's kind of like online inference that's going against. So there's online inferences going against these the events and features and saying like, oh, when they click on this, then we're going to show them this other thing, that kind of thing going on. But then these streams of events and features, they kind of funnel into like a lake house, right? So you can think of it as kind of funneling and getting pulled off of like a Kafka topic and then putting into like iceberg tables within an object store. And then inside there, there's kind of a separate decoupled process where people are going to be doing feature engineering. So they're going to be looking at these event tables. They're going to be looking at these feature tables. They're going to be looking at other tables that exist that kind of are perhaps like, Snowflake schema things, like kind of think about like TPCDS and look at the actual orders that they've placed and whether they were in the store or online, and different things about their demographics and stuff. And then they create these features, and then those features actually get stored additionally into as distinct feature tables within that kind of data lake house. And then so that's like one thing. There's the feature engineering, but then there is, when you go to do the training, there's something that's going to then extract and generate the different splits for the actual training workloads. And so often you'll be taking and combining some of these different features and then making them available. And oftentimes these splits will then be serialized into something like TF record or record IO, which are going to be far more efficient for the training engines to be able to ingest and read in. And then there's like a whole science to like the sizes of the splits, but generally speaking, these are going to be relatively large. Like TF record, they tell you to be in the megabytes to a couple gigabytes worth of range, which is great for realizing streaming bandwidth. But the actual number of splits will depend on whether you're using tensor parallelism, data parallelism, pipeline parallelism. If you're doing some of the techniques like they talk about, like in the GPipe paper, where they do like smaller batch sizes so that they can kind of shrink the bubble where GPUs are not busy. But yeah, you can see that like there's this whole process that revolves around recommendation systems, and it's a lot of data. And when there's a lot of data coming in, and then when you start to do the feature engineering, there's a tendency to try to preserve these features because they'll be useful, for training and developing different ways of doing inference. And in this paper right here, the link 1 here is a paper by Facebook, and they say that and this was a couple years ago, so maybe this is slightly changing, but these recommendation system models consume more than 80% of their machine learning inference, and at over half their training. So these are very big workloads. LLMs are kind of the rage these days, but recommendation systems, right? Whether it's recommending products, recommending kind of new articles, these are all over. industry and are a very demanding and interesting storage workload. And people have been using Ceph for data lakes and tabular data for a very long time. So it's a really, really good use case for Ceph.
Yeah, we had another question. Why train Ceph storage, or why train with Ceph storage instead of direct attach NVMe storage? That would speed up training by orders of magnitude. I think you mentioned that some of the local attach in the nodes are for rereads. And later in the presentation, I think you're going to talk about extremely large data sets in the tens of petabytes and higher. Any comments on local
Sure.
storage versus the Ceph? Go ahead.
Yeah, I mean, I think if we're looking at, if I go back here, right, and we're looking at these sorts of data set sizes, and you're doing a significant amount of data parallelization, like you can copy these data sets and do data parallelism across all, pretty extensively, such that you don't have to necessarily do the raw training off of a remote storage, right? And that will of course be faster, just because that's how physics works. When you're dealing with these, these training of like a recommendation system is going to be the amount of data that you would potentially need, depending on the size of your GPU system and how much data level parallelism you are. You might not be able to fit it all on the local NVMe storage of the system. And so in that case, you want the remote storage. Or if you want to have more flexibility because you're experimenting with how much data parallelism you're doing, or how you're doing your pipelining or something, to try to more maximally make use of the GPUs, and kind of having to readjust how the data, how you're partitioning the data and then preloading it onto all the local NVMEs. Maybe that's troublesome, right? So
Great. Thank you.
Yeah. It's always a trade-off, right? That's engineering, right? I also wanted to highlight kind of a, we've done demos, and there's actually like GitHub links if somebody wants to set up this sort of thing. But event-driven inference, in these examples we did it with X-ray imagery data, where you upload X-ray imagery to the Ceph object store. It generates a notification. That notification can then be then ends up in basically a Kafka topic that can then trigger kind of serverless processing. In this case, the serverless processing is actually applying inference to the image. So in our demo, it takes the X-ray image and then it generates a pneumonia risk score. And then that pneumonia risk score is then stored as a tag on the object. And then you could have additional notifications that, that have conditions on these tags or something that then, send off a notification to another topic that, alerts doctors or builds a list of imagery that, a clinician needs to look at, or something like that, right? And it doesn't have to be limited, of course, to X-ray images or even medical type things, right? This could be anything. It could be like a PCAP, and you've developed some sort of way of doing inference against it that finds naughty packets or something. I don't know, or you could do any number of things with this, but it's just an example of when you're injecting, or when you're ingesting objects into the storage system, you can trigger kind of events and serverless processing of it on, so as these things are coming in, you can then perform inference against the incoming stuff, and then make decisions and kind of chain off and do other workloads. And that's kind of a interesting use case that we've demonstrated, and then we've seen people put into practice as well. So yeah, why is storage important? Well, yeah, there's these data sets, there's all this data processing, both on the kind of analytical side, and then kind of creating the feature engineering, and then actually creating splits and doing the training, and then doing inference against the data, the data that is in the storage system as well. So storage is a pretty critical part of a lot of different machine learning workflows, and we put these up here just to give kind of a taste of a few, right? But there are a lot more that are involved retrieval augmented generation and LLMs, and it's a very fast and changing kind of environment. So it's rather exciting, the intersection of storage and AI/ML.
Great. So a question on what are the changes we're seeing on upgrading storage hardware with AI, and is it only the GPUs or are there other specific hardware? And I know later in the presentation you'll address compression, hardware compression, and also network scaling. So any high-level thoughts on that?
Sure. So I always kind of keep an eye out for what peers are doing in industry, and one of the things that I was looking into more recently to kind of inspire thoughts about Ceph hardware designs for satisfying these types of use cases was like Meta. So Meta, what Meta is doing from a storage perspective for its model training. If you read their their blog posts and their papers, is one of the things that they're doing is they're using their Yosemite systems, which are kind of like it's like a open compute style system, multi-node chassis, and then each of the chassis is like a single socket, is kind of like a single socket machine, and it has 6 NVMEs, and that 6 NVMEs with the PCI generation that they're using in them is kind of like a perfect match to 200 gig of network throughput. And so, the idea is basically to create this, to align it so that you have a simple system that just has a single socket, and then you have a number of NVMEs that can saturate the thing, and then you use, they're using a scale out file system like Tectonic. There are talks on this, and that is very similar resemblance to Ceph. And then they've developed a Fuse kernel client in order to make it easy for their AI ML kind of practitioners to just use kind of standard POSIX interfaces in order to do the actual training and that sort of thing. So I don't know, maybe that helps answer the question a little bit, but yeah, I think the idea is just like when you're picking hardware, right, you want to maximize the bandwidth, and so one way of doing that is just making sure that the geometry in terms of like the process, the amount of processor, the amount of SSDs, and the amount of networking that you provide is kind of completely streamlined to provide the maximum bandwidth so that we can hit these or satisfy these very data intensive workflows.
Thank you.
All right.
Yeah, go ahead, Phil. Take it away.
Yeah, thanks. So I was just going to say, let's think about the sort of underlying fundamentals of a storage system and its design, right? So I'm sure these kind of 4 pillars are quite familiar to a lot of the audience, but let's just go over them again and just kind of reiterate what they actually mean. So whenever you're building a storage system, it's all about balance. Like, you've got to balance the performance of it, how much data it can hold, how reliable the system is, and of course the budget. So when we think about performance, it really is a case of what does the application need? Like, you can build the fastest storage system in the world, but if you're never actually going to access that data, or you access it very infrequently, it just doesn't make any sense. So you kind of have to align the business value to actually the value of the data. As we think about capacity, the only thing that we ever see now in the storage industry is never anyone giving back storage space. It's always, can I have more storage space? The data sets are growing. Everything's getting larger and larger and larger. So one of the key things when you're building a storage system is that long-term view. Like, what a storage system looks like today is not what it's going to look like in 3, 5, 7 years time. So working with something that can handle that kind of scale, and then also in the rare scenario where people are willing to give capacity back, or they actually delete data, also scale back as well. That's something that Ceph's really good at. Reliability, like, this is super interesting. When you look at these very large systems, you can actually start tolerating quite a lot of loss. You take like an erasure coded backend. You can design it so that you can lose large sections of it. Like, as Kyle mentioned before, talking about Meta, they use a lot of erasure coding and actually power down sections of those storage systems to save energy. So there are lots of ways of kind of manipulating availability to reduce those long-term costs of storing petabytes and exabytes of data. And then finally, yeah, that cost side of things, it really is the sum of the three parts. It's just finding that real balance between having the right performance, having enough capacity available, and making sure that the data is actually available when you want it. It might not need to be available 24 hours a day, but sometimes some data sets are just accessed like that. You have to work out which one fits best. So then why Ceph? And I guess this is kind of the point of interest today, is why would you use Ceph? Firstly, for any kind of storage, but also for these kind of AI workloads. I kind of mentioned this before, but there's lots of different ways of accessing data. And that's one of the kind of wonderful things with Ceph. It's multi-protocol capabilities that have been around for years and years and continue to evolve. So let's think about block storage. So historically, Ceph supported its own RBD protocol. It is embedded or integrated into the Linux kernel, some of the virtualization solutions like QEMU, KVM. But also one thing that was kind of realized in the wider Ceph community was there are also other block protocols, right? So historically, there was a way of using iSCSI. That has now been deprecated because, of course, the world's kind of moved on. So now there's an NVMe over Fabrics gateway, which can provide you with an NVMe endpoint, just like any kind of proprietary storage system would. For the file side of things, Ceph has its own network file system called CephFS, super scalable. But then also, again, there's kind of industry standards, things like NFS, SMB. They've been around for years. They're kind of known and known quantities across the industry. And also with those things, with NFS and SMB, with Ceph, we can integrate with enterprise auth as well, so you can have very fine-grained control over who has access to what in those shares. And the other area in Ceph, and honestly, this is where we see the largest growth with Ceph in the industry, is really around object. Ceph supports the AWS S3 protocol out of the box. It also includes some of the advanced protocol features as well around identity and access management and the STS API. So that's the security token service. And that gives you very tight-grained and kind of time-limited access to individual buckets within the object store. You can also provide an NFS share from an object storage bucket as well. This is another way of kind of using a traditional approach to access something that's more modern, like object storage. Not all applications can speak object, so this is like another kind of entry point into this new sort of scalable world. And I think kind of the way that I always describe Ceph to anybody I talk to is, and if it's the one thing you remember today, it really is the Swiss Army knife of storage. It has an answer for all of the things that you need to do, just from that one single tool or one single cluster. A few moments ago, we did talk about some of the networking stuff, and I'll kind of dive into that. But if we think about when you're building out a Ceph cluster, there's from a hardware perspective, there's kind of three main areas that we tend to think about. So the systems themselves, they need some compute, they need some working scratch space or memory. So those two components are super important. Obviously, it's a software-defined storage system, so naturally, like most pieces of software, higher clock speeds do help. There are some parts of Ceph that's still kind of single-threaded, so higher clock speeds certainly help for some areas. The more RAM in a system is great. During kind of rebuild operations, when something is broken or failed and you're kind of rebuilding around it, you do see sort of increases in demand for additional memory. But then also you can configure Ceph to have a read cache as well. So depending on how you're accessing the system, that is, but you can use the RAM in those systems as a read cache as well, just to kind of accelerate any kind of rereads that have not managed to be locally cached in some of those GPU nodes. The network side of things, Carl kind of mentioned this about not having this really balanced environment, not having a machine that's got tons and tons of local performance, but like a 10 gig pipe. That's not the kind of thing you want to do. it's gotten to the point now where 100 gigs kind of everywhere, multiples of 100 gig kind of everywhere. So finding that balance between the actual throughput within the system and what the network's capable of, and then kind of sizing those machines based on that network throughput, that's definitely the best way to go. And kind of the other thing to think about as well, with Ceph, we have an internal network, we have an external network. So the internal network, that's where we do all the replication, the protection of data, those kinds of things. And then the external network is obviously for client access. So those two are typically very, very segregated networks. We don't want those two sets of traffic to kind of interfere with each other. And then finally, Ceph is this hardware agnostic system. We can build systems that are kind of capacity focused with spinning disk. We can build like mid-range storage systems with SAS attached SSDs. And now as we get into this kind of continued evolution of NVMe, where we have large or high capacity NVMe devices, as well as the super fast NVMe devices, we can use all of that different type of media within a Ceph cluster, depending on the kind of needs of a particular pool or data set. And then the one thing that I think I've personally mentioned a bunch of times already is this idea of scaling. So to kind of illustrate what happens with Ceph and how it scales, let's take this sort of theoretical 4-node cluster. So let's imagine, well, I say imagine, this is actually from test data. So this is a cluster we could read 20 gigabytes per second from. And now we've talked about this whole idea of, as a Ceph cluster grows, you add more nodes to it. The performance continues to increase in kind of a linear fashion. So let's double the size of the cluster. We've now got 8 nodes instead of 4. We're able to double the read performance from that cluster. And we kind of continue with these steps. We double again, we get to 80 gigasecond. We double again, we're up to 160 gigasecond. The one thing to remember, and both of us have mentioned it now about networking, this is really building a highly performant Ceph cluster is now like a networking planning challenge. You don't want to end up with a situation where the network itself actually becomes a bottleneck, and you've kind of got this fast hardware, or any kind of hardware that's then bottleneck is a really it's just poor planning and bad design. So you do really have to think about this longer term scaling if your data set is going to grow over time. And there's also a fantastic example, like here I'm talking about scaling from sort of tens into hundreds of gig per second. From one of our friendly organizations in the community, Clyso, they have a great story on the Ceph blog where they managed to scale a Ceph cluster up to 1 terabyte per second. It's a fantastic read. Took a lot of hard work from the team. So yeah, if you get the time and want to find out more, definitely take a look at that. And then in terms of accessibility to Ceph, Ceph has been around for an awfully long time now. The last time I checked the OpenStack user survey, the statistic was that something like 70% of production OpenStack environments use some form of Ceph for storage within. And that's not just for AI workloads. That's across all sorts of enterprise IT infrastructure. Within my organization, internally, we use Ceph as the backend storage within our internal clouds. It's used across so many different organizations, thousands and thousands of different organizations across the world. So if kind of some of the stuff you heard so far is kind of interesting and you want to find out more, Ceph is, of course, fully open source. Ceph.io is kind of the homepage. It's where you can find everything about Ceph. Code is on GitHub. You can go and inspect it, download it, build it, whatever you want to do with that. And then, of course, the upstream docs are absolutely fantastic in one, explaining all of the different features and functions, but also kind of how to get started as well. And there's loads of different ways of doing that. From all of the downstream vendors, there's lots of different approaches as to how you might want to deploy a Ceph cluster. So definitely kind of do some research about what we all do and what we all provide. Of course, nothing comes without its challenges, and especially as you want to, like, if you take you experiment with Ceph and then you want to scale it over time, you might run into kind of challenges along the way. There's a very active community mailing list. I saw one question earlier from someone who's very active in the community. So hello to you. That's definitely one area where you can get help. There's also this ecosystem of vendors and practitioners who can help provide downstream code, but then on downstream binaries, but also provide sort of the consulting services around Ceph and kind of understanding the best way of deploying it, the best way of scaling. And I just kind of want to reiterate, this idea that yes, AI has high bandwidth needs or high throughput needs of a storage system. I think the real thing to think about is actually it's more about planning and design than just needing a specialized storage system. And then one last thing that I wanted to talk about is really around this idea of storage efficiency. So over the last couple of years, upstream Ceph has introduced, maybe not even the last couple of years, longer term than that, there's been features within Ceph to be able to compress data that's stored within the back end of a storage system. So whether that's data that's passed through the router's gateway, so that's the S3 endpoint, or is just stored in a blue store pool. So blue store is kind of the back end of a Ceph cluster. There are a couple of different areas where we can apply compression in that system. The last couple of years portion comes into this kind of pluggable framework where if you have a hardware accelerator, you can then start to offload some of that compression workload to help alleviate some of the CPU overhead that you would see. So if you take a look at these charts on the right here, you can see in the leftmost column that's no compression for both read and write workloads, and then you can see in the middle there that's when that data set has been compressed using the zlib or zlib compression library, and you can see there's quite a significant decrease in performance, and this is obviously just relying on the power of the local CPU. Then the right-hand side, you can see where we've been able to use some hardware offload, and you can basically see that there's almost no impact by using hardware offload. So in this example here, this was Intel's QAT or Quick Assist technology. So that's a feature that's available on die in Intel's modern CPUs. Historically, there are also options to do this on PCIe cards. There are other options out in the market as well. And as kind of the interest kind of again comes back to adding in these kind of additional hardware offloads, they can be integrated into Ceph, so it becomes quite an easy thing to turn on, kind of reap the rewards of compression. And it's quite funny, I've talked about this subject a few times recently, and it's quite funny. You think of compression, it's kind of boring, but actually, when you look at the savings you can get, so take something like textual data, CSV data, we see that being compressed usually around 25% in terms of a reduction of raw space used. Take raw video. Raw video is crazy. With raw video, we see up to a 60% space reduction. Obviously, that's not something that's already been run through a codec. Once you've run a raw video stream through a codec, you're not going to see any savings from compression. But for that raw data, if you want to, that's the data set you want to keep. We see these kind of huge savings. And of course, what that means is you can build then a smaller cluster, so there's less upfront capex. But then also a smaller cluster means there's less machines in a data center, it's less power draw. So the ongoing kind of OpEx savings are quite good as well. So I think at this point, we're going to take a look at another use case. So I think back to you, Kyle.
Great, thank you. Kyle, go ahead. Yeah.
Oh yes, so this is just kind of an example system that we have put together here, and yeah, it's just some conventional dual socket configuration with a little bit of memory, a couple 100 gig links, and some TLC NVMe drives, and kind of giving you a slight gauge on the amount of bandwidth that you might be able to see with it. And as Phil kind of outlined in the scaling slides side of things, as you demand more aggregate throughput, you can kind of increase the quantity of this. When you're thinking about, scaling for these workloads, is often you often want to try to understand what the ratio is of throughput to capacity, and then that'll help you determine how many SSDs you put in the system, right? So if you have more of a capacity biased, then you could use something where you have 24 TLC drives and then a 2U chassis, and you can use kind of the denser SSDs 15, 30, or even 61 terabyte these days. If you're trying to, if you're doing just LLM training or something, you might, pare that down to more like the meta configuration that I described earlier, where it's a single socket, some memory, 200 gigs, and then six high speed Gen 5 NVMe's or something like that. On the networking side, right? So this is something that we encounter a lot with people on where they go, I had some hardware that I, cobbled together, and I was running Ceph, and I don't like the performance that I'm getting. And it really, when you're doing a distributed system like Ceph, scale out system, its lifeblood is basically the network, right? So and one of the most common issues that we see is where there's far too much oversubscription in the bisection of the cluster, right? So if you have a cluster that's distributed across multiple racks, and say you have 20 ports or something of 100 gig going down to the servers, but then you only have 200 gig uplinks. Now you've created this 10-to-1 oversubscription, which is very, very, very high. And so when we're trying to decluster and place replicas or erase coded chunks, across hosts or across different racks, that network bisection, that oversubscription is going to be the choke point for the cluster. And so, if you really want to build a high performance Ceph cluster, you want that oversubscription to be as low as possible. You want it to be 1-to-1 or 1-to-1, or even in the most extreme cases 2-to-1 or something. Right, definitely not 10-to-1. 10-to-1 is if you look back at the GFS paper, right? The reason why they were doing the locality optimization for MapReduce was because they had these, they were using archaic switches that they could only do 12-to-1 oversubscription or something. We're not in that world anymore. You can totally build non-blocking fabrics that have 0 oversubscription, and even then I'll also add that on the training cluster side of things, they're doing things where they actually have negative oversubscription, so that even if links fail, they don't have any oversubscription, right? So that's how demanding these sorts of workloads are. And so you absolutely want to have ample network connectivity, and you don't want to be choking out your storage system or your training clusters by having an inadequate bisection. All right. And yeah, if you guys want to learn more about Ceph, right, there's a bunch of resources in the community. There's Ceph.io. There's always a bunch of really cool blog posts that are going on there. We have some upcoming events. Actually, we just had a Ceph Day event in India that was earlier this month. In March, we will have one in San Jose, hosted at Almaden Research Facility. And then we have one planned for later this year in London. And of course, we have a kind of a yearly get together technical conference called Cephalicon. This most recent one was hosted by CERN in Geneva, Switzerland. So if you're interested, the slides and recordings are online. And yeah, of course, wonderful SNIA. They have an education library. There was a previous talk given by some colleagues and friends from the Ceph community, and that's available as well.
Awesome. So, any last takeaways? Phil, was that?
Yeah, I'll dive in. I think it's really funny. When I started working in the storage industry, pains me to say almost 20 years ago, it was super hidden. And it's really funny, even now, the storage element in any kind of like infrastructure always seems to be kind of like hidden away, and it's always a bit of an afterthought. But I think what's becoming more apparent in this like high cost scenario where GPUs are crazy expensive, you actually have to be able to feed them data. So there's been this like awakening about the storage system that actually provides that data into these kind of environments. So it's great to see that. So yeah, just to get the best TCR out of that massive investment, you also have to invest in the storage as well. You know, I keep saying about Ceph scaling, the way that it is possible to piecemeal grow a Ceph storage cluster, adding a few nodes at a time over an elongated period of time. Those nodes don't even actually have to match in configuration. Of course, what you buy today is not what you're going to buy in 6 months. It's not what you're going to buy in a year. So having that heterogeneity and the support for that within Ceph is fantastic. As Carl mentioned, the networking side of things, like it's the interconnect has become like the Achilles heel at this point. The planning of the network is super important. And then finally, I think that idea of having this kind of ability to bring in different optimizations into Ceph. So right now, there's this support for Intel's QAT, but then what's coming next? Who's going to bring some other hardware accelerator that can also bring in more optimizations in the future? And being able to kind of take those into this open source system and make use of those different types of hardware is fantastic.
Awesome. Great. So right now is the Q&A session. We literally have 3 minutes. And so if we could do one question, there was a question about the significance of IT administrator roles and the future kind of professional growth. And I think your comments about planning and education and this network scaling, et cetera, would be critical. But any last comments? We've literally got 2 minutes now, so go ahead.
I think, so again, thinking back in my career, when I started, there was this whole idea of you were like a storage professional, there was a virtualization professional. And I think what we're seeing now is actually you have more the IT generalist. And that's possibly like a good thing because the tech has advanced to a point where you don't have to be super specialized. I would say that in the open source world, it is a bit more complicated. It's more like being a true sysadmin rather than like a storage admin. But yeah, there's the way that the tech has become easier to use. It's easier to consume. The long-term like career growth there is actually being more of a generalist and being super or hyper focused in one area.
Yeah.
Great. Go ahead.
I was going to agree. And like, one of the things that like I do from a storage practitioner perspective is like when there are kind of new and exciting workloads, one of the things I'll do is I'll like go and look at the body of research for, like I did this for like analytics, where I go and I grab all the different seminal papers that talks about the different things in that kind of development. I print them all out, I organize them chronologically, and then I would just read through them, all of them, so that I know, like I understand like the progression of why people are doing things and why we are at the current, why the current state of the art is the state of the art, right? Because like people always say like, oh, well, what is the best practice? So it's like, well, the thing about best practices is they're always just practice, right? We're always trying to get like figure out what like the next best practice is, right? So it's like, it's always like a fluid thing. And if you do that, I think that understands like, where we've been, where we are, I think is important. And then like, I've been doing that more recently with like AI. So, going through, getting all the kind of seminal research, putting it all out, printing it out. A lot of it has all this math that I don't understand, but you know what I mean? But there are still things that you can, you understand, you connect, you understand about the distributed systems, and the better you have understanding of the workloads that you're catering to as a storage administrator, the better you'll be able to have conversations with your end users and really understand their needs and wants, and then how to construct the storage systems that are going to satisfy those needs.
Okay, great. I have 40 seconds or less. So thank you very much to our presenters for the expertise and insight. This has been a fantastic discussion with excellent information, and we will have a Q&A blog that will go through all of the elements of the questions. There were many questions that were answered directly through the chat, but we'll bring all those into the Q&A. And also, thank you to the audience. Thank you for joining us. Please remember to rate this webinar, as this is very important to get your feedback, which helps us create better educational material. Also, please remember you can always download this presentation and many other items at our educational library, as well as follow us on Twitter. Thanks again to everybody, and have a great day. Thank you. Bye-bye.
Thank you.
Thanks all.